All right, so here in this video, we're going to look at just what is the period of a simple harmonic oscillator. Okay, so one thing to remember, and we talked about this a little bit in the last video, is that the motion of a oscillator is periodic, which means the motion is going to repeat it in equal time intervals or intervals of time. Right? Think about periodic. In schools, they have periods, right? And so what does that mean? It means every so many minutes the bell rings, you move to the next class, right? And so that's what we talk about being periodic. So the oscillator is going to do something every so many seconds, every so many minutes, and so forth. Okay. Now the period, okay, we talk about periodic motion. So the period, which is abbreviated capital T, of a simple harmonic oscillator is the amount of time required for a complete oscillation. And a complete oscillation is to go back and forth. So if it's a pendulum, it's to go from one extreme to the other and then back to the original. If it's a spring, it's down and up. So it's going to go down, come back up to that original position, right, for where you started. All right. Now, period, because it is a specific time, it's going to be measured in seconds. One way to think about period is that, and I'll write it down here in a couple bullet points, but it's seconds, okay, per cycle, right? And so on the other side of it, we have the frequency, which is abbreviated F of a simple harmonic oscillator, is the number of times there and back oscillations per second. So the amount of times it goes up and down per second or back and forth per second. Okay. It is actually measured in what is called hertz. If you're interested in computers, right, the calculation speed of a processor is in like gigahertz, megahertz, terahertz, okay, stuff like that. That is how many times like it does the cycles per second, right? Now, period and if I write cycles per second here, what you see um, is that they have an inverse relationship. Okay, so they're going to work again. They work opposite each other. All right. Now, the equation for period is simply T equals 1 over F, right? So it's the inverse of T of F, which makes the equation for period or for frequency 1 over T. Okay. A lot of times what they'll do is they'll say, like, let's say, in the water, right? A buoy bobs up and down 10 times in 5 seconds, right? And so if you're given information like this, you can easily find the frequency. You can also find the period, right? By understanding these two things on how they work. All right. So if I want to find the period, it does 5 seconds, you know, 10 times. So my period would be half a second. My frequency, it goes 10 cycles or 10 times in 5 seconds, right? It's 2 seconds. Well, or sorry, not 2 seconds, but 2 hertz. Sorry about that. Unit for frequency is hertz. So what does that tell me? Like half is 1 over 2, right? It's an inverse relationship. All right. So let's now, because pendulums and masses on springs are simple harmonic oscillators, they actually have their own equations for period. So the period of a pendulum is 2 pi square root of L over G, right? L is the length of the pendulum, okay? G is the acceleration due to gravity. So let's just say something that you could be asked on a test is how can we confirm the acceleration due to gravity on Mars? Well, the simple thing to do is take a pendulum up there, measure how long it takes to go back and forth. And if you know the length of that pendulum, you can then trace it back to the G value. Okay. The spring is going to be 2 pi square root of m over k, right? And so mass attached to the spring is our m, and k again is that force constant. I'm going to write these next points in a different color. So note that pendulum has no mass dependence, right? So if I took a 1 meter long string and I put a kilogram, 500 pounds, a little child, they're going to still swing at the same period. Okay. And then on for the spring, there's no stretching or compressing dependence, right? Or elongation. Okay. So if a question talks about what happens if I double the amplitude, right? There's no effect about onto the period. It's the spring and the mass, right? That's the only thing that matters. Okay. Now let's look at a couple example problems here. Actually, there's three here. The first two are multiple choice questions. So this is an object of mass m is attached to a spring with constant k, oscillating with amplitude a. Assuming air resistance and the mass of the spring to be negligible, which of the following changes alone would cause the period of this oscillation to increase? So I have a mass spring system, so I know my period is going to be 2 pi square root of m over k. And so if we look at the relationships, right? So t is directly proportional to the square root of m, but it's inversely proportional to the square root of 1 over k. Okay. So for example, if my um, two ways I can increase t, right? What are the two ways I can increase t here? Is I can increase the mass, that would increase my t, right? I can also decrease the k, and which would increase my t. So that's what I'm looking for in my cases, right? So look at case one, increasing mass, check, right? That's this scenario right here. Increasing a, what did we say right before we came here? There's no dependence on the amplitude, okay? Using a spring with a greater k value. Well, for me to increase my t, I need to decrease my k. So that one is out as well. So what's the only answer? Choice A, right? And so remember these relationships. And if you look at the pendulum, t is directly proportional to the square root of L, but it's also inversely or proportional to 1 over G. Okay. So if I want to increase the period of a pendulum, I do one of two things. I make it longer, or I do it somewhere else with a smaller G value, right? Take it up to the moon. If I have a 1 meter long pendulum, this is actually a one. Sorry, I was going to make that into an L. Automatically, I see the pendulum form. I want to make it into an L, right? But it's a one, right? So if I have something up on the moon, right? If I have a 1 meter pendulum here versus the moon, it's going to be longer on the moon because of the gravity. Okay. The next one says the sphere of mass m1, which is attached to a spring, is displaced from its equilibrium position as shown below. I forgot to put the picture. Basically, the picture looks something like this, right? And then you have a pendulum doing its back and forth motion. A massive M2, which is suspended from a string of L, is displaced to the right as shown below. It's up right above, I just drew it, and released from rest, and so it swings as a simple pendulum with a small amplitude. Assume that both spheres undergo simple harmonic motion. If both spheres have the same period of oscillation, which of the following is an expression for the spring constant? All we have to do, right, take the two period equations and set them equal to each other. So 2 pi square root of m over k is going to equal 2 pi square root of L over G, right? 2 pi's will cancel out. And so if I square both sides, essentially the square roots cancel out. So I end up with m over k equals, and this is going to be m1 because that's the mass attached to the spring, over L over G. And all I got to do is the algebra to solve for this, right? So I'm going to multiply both sides by k. So it's going to be M1 equals K L over G, and I'm going to multiply by G over L, right? And so my K value is going to be given by K equals M1 G over L. I forgot to write the L here, right? And so that's what I'm looking for, which is going to be choice C. All right, and now the last one's going to be an actual calculation question. So a simple pendulum is used to determine the G value, uh, acceleration due to gravity at the surface of a planet. The pendulum has a length of 2 meters and the period is measured to be 2 seconds. What is the acceleration due to gravity of this planet? So this is a good question because of the solving for G. You do have to be careful. So the first thing I'm going to do is I'm going to divide both sides by 2 pi. So I end up with T over 2 pi equals L over G, right? Sorry, square root of L over G. Now I'm going to square both sides. Put the 2 in the wrong spot, should go over here. So I'm going to have T squared over 4 pi squared equals L over G. Um, you may want to memorize this kind of relationship, right? Because it's very helpful. And now I'm going to solve this for G by simply multiplying both sides by G. And so I end up with L equals GT squared over 4 pi squared. And then I'm going to multiply both sides by 4 pi squared over T squared. Right, and so I end up with G equals 4 pi squared over T squared. Now, when plugging this into the calculator, this is going to be your common mistake, is not squaring the pi, right? Or even squaring, T. So it tells me, sorry, I forgot my L. It's 4 pi squared L, right, over T squared, right? And so we say 4 pi squared times 2 over 2 squared. Again, be careful, make sure you're squaring pi and you're squaring T. Okay, basically that's going to go, and this, for this problem, the 4 on top is going to cancel the 4 on the bottom, and I end up with just something 2 pi squared, which is going to end up being 19.7 meters per second squared. And so that would be my G value on this hypothetical planet. Again, this is what we would do if we want to go up to Mars, right? And confirm the G value on Mars. We take a pendulum of a known length, record its period, and then we figure out the G value. Okay. NASA's done a great job here on Earth, but if we ever get onto Mars, we can confirm it, right? Or see how close they got to it, right? Then we can do other things, cool things about calculating, the densities and stuff like that of planets. Right. So the next video is going to focus on energy of simple harmonic oscillators, which is going to be the last topic in this unit.